Method of characteristics. What can go wrong? So we consider our quasi-linear PDE with initial conditions given in terms of an initial curve. So here is our problem. Find a solution U for this system. And we are interested in the well-posedness of this problem. So we ask if the solution exists, if it is unique, and if it is stable with respect to the initial conditions. We will skip the stability issues in the following. Let us look at our well-posedness problem in the XYU space. So here is our initial curve. We now use the projection from XYU space to XY space, let's call it pi, and we project the initial curve to the XY plane. Now let us consider characteristic curve emanating from point S on the initial curve. We also consider its projection to the XY plane. This is a characteristic starting from the point pi of gamma S. But things happen when a characteristic is tangent to the projection of the initial value curve, because in such case the characteristic curve slides along initial value curve, and in this way one cannot weave the solution. One cannot go outside the initial value curve. This leads to the following definition. A quasi-linear PDE star and the initial condition double star represented by the initial value curve gamma S satisfy transversality condition at the point S on the initial curve gamma of S if the characteristic emanating from the point pi of gamma S intersects pi of gamma S non-tangentially. This condition can be effectively checked in the following way. If XYU are coordinates of the characteristic curves, then the tangent vector to the characteristic at S is dx over dt evaluated at t equals 0. So these are the coordinates, right? And dy dt at t equals 0. And is nothing because of the equation of characteristics like A evaluated at the point x0s, y0s, u0s, and B evaluated at the point x0s, y0s, u0s, where A and B are the coefficients defining the quasi-linear PDE. On the other hand, tangent vector to the projection is given by dx0 over ds, dy0 over ds. Remember, our initial condition was therefore the characteristic, which is this thing, is non-tangential to the projection of the initial value curve, which is this thing, if these two vectors in xy plane, this one and this one, are linearly independent. Therefore, the condition of non-tangentiality means that the following Jacobian is not equal to 0. Obviously, when the transversality condition between the PDE and the initial curve is not satisfied, there will be problems. So what can be really guaranteed by 100% for our problem of quasi-linear PDE with the initial data? We have the following theorem. Assume that the coefficients A, B, C of the quasi-linear PDE are smooth functions in the variables x, y, u in the neighborhood of the initial curve. Further assume that the transversality condition holds at each point S in the interval on the initial curve. Then the problem of finding function u of x and y satisfying the PDE and the initial condition has a unique solution in the neighborhood of the initial curve. On the other hand, if the transversality condition does not hold for an interval of S values, then the problem has either no solutions at all, or it has infinitely many solutions. We illustrate this theorem on a number of examples. In the first example, we show what happens when transversality condition doesn't hold. This example is very simple. It concerns with the equation like that, with the initial condition. So here g of y is some function. So we want to solve this equation by the method of characteristics. So first we just look at the initial curve. And we consider the usual Jacobian to see if the transversality condition holds. So here is A, here is 0. Now the x over the s is 0 and the y over the s is 1. So this determinant is equal to 1. It is definitely not equal to 0 everywhere. So we shouldn't expect any problems. And indeed, if we just solve the characteristic equations, then we get the following formula for the characteristics. And because of this Jacobian being non-zero, this transformation t to x and s to y, or x to t and y to s, can be inverted to get t equal x, s equal y, and the general solution then is x plus g of y. So we have no problem at all. The solution exists and is unique in this case. But what if we just change initial conditions to the following form? Where h of x is now some differentiable function. So now the initial curve gamma of s is And now the Jacobian, which should be examined for transversality, looks like 1, 0 as before, but now derivative of x is 1, of x with respect to s is 1, but derivative of y with respect to s is 0, and this Jacobian is 0 everywhere. So here we expect problems. Indeed, when we solve this equation with the new initial conditions, we obtain, using this general solution, we see that u of x0 is x plus f twiddle of 0, and we want that this satisfies initial condition h of x. So we see that it is only possible if a given function h of x is linear in x. So if h of x is not equal to x plus some constant, but is some other function, then this equation with this initial value problem has no solutions at all. It has only solutions when h of x is x plus c. If this is the case and h is like this, we can show that actually the equation has infinitely many solutions. One can check that u being x plus c plus f of y, where f is arbitrary differentiable function of one variable such that f of 0 is equal 0, we can see that this is a solution to and actually here we have infinitely many solutions because they depend on arbitrary function f of y, with the only requirement that this function vanishes at 0. So in this example we saw the situation when the transversality condition is non-satisfied everywhere, and because of this, initial value problem for a PDE either has no solutions at all or has infinitely many solutions. In our next example, the transversality condition for a PDE and its initial condition will not be satisfied only in one point, and we also will see that there is some trouble there. We consider a PDE with an initial condition. So let us write down the initial curve. And now the Jacobian to see the transversality criterion is 1, 1, which is a and b of our equation. And now dx over ds, which is 1, and dy over ds, which is 1 plus 2s. So if we calculate this Jacobian, we see that is equal to 2s, and it's non-equal to 0 everywhere except when s is equal to 0. So it is 0 if s is equal to 0. So the really trouble on the initial curve at its parameter value s equal to 0. If we write the equations for characteristic curves, which is just x1, y dot 1, and u dot equal 1 minus u, we solve for the characteristics, and we'll get here in this solution I already inserted initial conditions. So this is the solution for characteristic curves. And now from the first two equations we can see how the characteristics look like in xy plane. We find that characteristics looks like which means that they are straight lines on xy plane with the slope 1. So these are the characteristics. And now, if we try to find explicit formula for the solution as u equal of u of xy, we simply see that from here we get that s squared is equal y minus x. So taking square root, we get s equals square root of y minus x. And then we can insert it to this equation, obtaining the solution in the form. Okay, so that's our general solution. So here is our xy plane. I plotted a number of characteristics. So let us plot also the projection of the initial value curve. We see that the initial value curve is just here. So it is y equal x plus x squared. So this initial value curve is a parabola with zeros in 0 and minus 1. It looks like this, right? If one looks at this picture, one sees that in general this red curve intersects the characteristics transversally, except perhaps in the point x equals 0. So let us calculate the tangent vector at x equals 0 to the projection of the initial value curve. So this projection curve is just y equal x plus x squared. So its slope is this derivative with respect to x. So it is dy over dx, which is equal to 1 plus 2x, right? And one sees that when x is equal to 0, the slope of the tangent vector to the initial curve is equal to 1, which is precisely the slope of our characteristic at that point, because characteristic at that point looks y equal x, and again this has slope. This shows that this transversality condition is not satisfied at x equals 0, which we actually already know, because this precisely corresponds to s equals 0, as we have seen from the Jacobian. And because of this lack of transversality at this point, the solution is not unique, and this not uniqueness is apparent in here. At s equals 0, when the initial data is not transversal, the square root of y minus x changes sign. We could have chosen another sign for s here, and then inserting such s equal minus square root of y minus x into u, you would get another solution in the vicinity of x equals 0. So the solution in the vicinity of x equals 0 is not unique. And the reason for that is that the data are not transversal to the characteristics at this point. And I stress that it happens in the situation where the equation has very regular coefficients and the equation is linear. Before passing to the third example, let us make a comment on linear PDEs. If the PDE is linear, then the coefficients a and b do not depend on u, and the appearance of u in the coefficient c is only linear. If one wants to solve this PDE by the method of characteristics, then one has to write equations for characteristic curves. And these equations, although the original PDE is linear, in general are nonlinear. We know that if an ODE is nonlinear, we have to assume certain conditions about ODE for having warranty that it has a solution and that this solution is unique. Thus, if coefficients a and b are quite nonlinear functions of x and y, we cannot expect existence and uniqueness of a solution of a PDE even in the linear case. Our third example will illustrate these issues. We consider a PDE of the form with the initial condition, and we want to solve it by the method of characteristics. First, let us write the initial curve, and let us see if we have any kind of transversability issues. So we consider the Jacobian J of the 2 by 2 matrix, which first row is a and b of the equation on the initial curve, so it is 1. And since on the initial curve y is equal to 1, so it is the coefficient b is equal to 3. Now dx over ds is 1, and dy over ds is 0, but this determinant equal to minus 3, which is definitely non-zero. There is no problems with transversability. Okay, so now we want to solve characteristic curve equations, which are, and this equation has general solution as, and knowing this, we can write the solution for characteristic curves satisfying our initial conditions. So these are our characteristic curves, and from them we can get characteristics. Since t is equal x minus s, so the one parameter family of characteristics is obtained by. So the characteristics here are curves like this. Here is cube, and so on. So here are our characteristics. Now let us plot our initial curve, which is here. So it is y equal 1 line. This is our initial curve, and as we already saw, there is no any transversability issue with this initial value problem for the PDE. Nevertheless, there is a problem. The problem is that the equation, this one, for characteristic curves, has a singular solution y equal to 0. So the line y equals to 0, which is this one, is also a characteristic. The appearance of this additional characteristic is related to this, that this ODE doesn't satisfy Lipschitz property. It doesn't have unique solution. The solutions to this ODE passing through y equal to 0 are either these cubic curves or a line y equal to 0. Therefore, we may expect that the solution to our problem will have troubles at line y equal to 0. And indeed, if we invert this, we get and S. Which gives a solution, and this solution is non-differentiable at the line y equal to 0. And the reason for that is that the ODEs for characteristic curves do not satisfy Lipschitz property.